get started in a minute or two. People come back from lunch. Thirty seconds. Can I speak to the room host? Is he here? Is she? Not here. All right, good afternoon, everyone. My name is Bruce Momjian, and I'm raring to go. I am one of the Postgres core team members and have been working with Postgres since 1996. I work for Enterprise DB, one of the Postgres support / product companies, and I'm excited to be presenting to you a tutorial about common table expressions for the first half and window functions for the second half. This is a 3-hour tutorial, goes till 4:30. We will take a break in the middle, probably between the two presentations, pretty much 20 minutes or so, and kind of give you a little chance of decompressing as we move from one topic to another. The reason I'm excited about this talk is it takes probably the two most powerful sort of advanced SQL features and presents them in a single talk. This is an excellent talk for people who are doing a lot of development work using databases, application development, data warehousing, analytics, that type of thing, and gives you a good sort of launching pad to understand how you can make the best use of your SQL database. Now, all the examples I'll be talking about actually are related to Postgres. We've had these features for several years, and in fact, probably 5 or 6 years. I have been told this morning that MySQL implements a lot of these features as well. In fact, Dave, can you address that at all?
We've recently added CT to MySQL, which is test release right now.
Okay, so I'll just repeat what he said. He said MySQL has had CT since when? I'm sorry, 5.8?
No, it's coming out in version 8.
CTEs are version 8 or window functions?
Both.
Window functions and CTs both in MySQL version 8. Okay, great. So as I understand, you used Postgres' features as an example. So what I'm showing you should work in both databases. And in fact, these are SQL standard features. So if you're using any SQL standard database that implements the SQL standard for these particular options, you should be able to use them very capably. Yes, sir?
Is Maria downstream from MySQL, or are they completely for it? So this wouldn't affect what they're doing, whatever they're doing. Ironically, is that we tested their benchmark Postgres and our stuff and our the best. And Maria is the first.
Thank you, Dave. Again, this is really two talks. Again, both of them have a similar theme of making the most use of SQL and the current sort of standards that have been adopted in recent years. The slides that you're going to see actually are on my website. So this website right here is actually a place you can download the presentations. if you have a desire to do so. And I'm going to go down for a minute, and I guess that's just, let me see if I can focus this a little better. Is this a manual focus? I guess it is. Oh, no, that's just the zooming. Okay, anyway, that's probably as good as we're going to get. But again, feel free to download this presentation, as well as the other one. There's really 20 or 30 presentations here on that website related to Postgres. And also there's some security talks, and many of them have videos. So if you find something interesting, you may find there's a video that goes with it, and you can hear me droning on and on about these particular features. Again, we will take a break between the two presentations, and again, this is ideal for developers. Now, there's two ways I can present these talks, and I'm going to take a little poll of the audience to decide. One way of presenting this talk is for me to be speaking and you to do Q&A. I ask questions about how certain things are handled or how would I implement certain things. In that particular example, we would basically talk about some slides, again, take questions as we go, talk about some more slides, take questions as we go. We wouldn't take any breaks for you to actually practice some of these features. Okay, so that's the first one, where we do mostly Q&A. We don't take breaks for you to actually practice. The second option is where we will take breaks after each section, maybe 5-10 minutes, to give you a chance to actually practice the features that you've already seen. Now, of course, because these slides are already online, you can almost cut and paste the examples into PSQL or to pgadmin for you to kind of practice it. So the question I have for the audience, and I'll look for a raise of hands, the first option is all Q&A with no breaks for actual hands-on. The second one is for breaks for hands-on. So how many of you would like no breaks for hands-on and do all Q&A? Okay, that's about 10. Okay. How many people would like to take breaks so you can practice what you're doing? Okay. I think the first group won by a slight margin. Sorry for that. What we will do is that 20-minute break that we take in the middle, that'll be your chance to practice the previous section. And, of course, I'll be here at the end. If you want to take another 20 minutes after to practice, I'll be glad to stick around to do that. So that's how we're going to kind of work it. Again, some groups, I've done this twice. One group chose the one almost universally, and the other group chose the other universally. But, again, it has to do with type of audience you have. Again, this is a tutorial, so any questions you want to ask, feel free. Yell out, raise your hand, whatever you want to do. Does anyone have any questions before we get started? Yes, sir. You can't find the presentation. Okay, so if you go here, this is actually under SQL. There's an SQL sub-tab under presentations. That's correct. Yes. That's exactly what it says up here. Right? Okay. And again, the reason for the confusion, he's right, is that when I took the two presentations and combined them into tutorial, I couldn't say programming the SQL with common table expressions and Postgres window function magic. It would just be too long. In fact, if you go look at the screen, the title doesn't fit on the screen of the scale event. It kind of just goes to dots because it's too long. So that's why it kind of got compressed. Other questions? That's a great question. Okay, great. Okay. I do think you're going to get a lot out of this. I really enjoy these talks. These two topics are really kind of close to my heart in terms of really empowering developers, because a lot of developers have a tendency to look at databases as a key store or as just a data store for them, and when they approach a database, they're just basically thinking, okay, I'm going to put the data in, I'm going to get it out, and everything that I want to do, I'm going to do in my application. That is the way we did it in the 80s and 90s. That is no longer the most efficient way today, but it might be the way you did it in the past, or that might be the way you were taught in college, okay? Or you might have worked for an organization that did it that way. And frankly, if you're using a relational database as just a data store, you're really not getting the full benefit out of the database. And the reason is because these databases now, using the current SQL standard, are really giving you a whole tool set of things that make your life easier as application developers, okay? It doesn't make sense for you to re-implement a whole bunch of things in an application and perhaps implement it over and over again in different languages in different applications, when you can actually structure what you want as an SQL query and give your problem to the database, right? Give your problem to the database, let the database solve your problem, and give you the results that you want. And that's, I think, the major theme I'm going to be talking about, not only with common table expressions, but with window functions. The idea that you can now give your problems to the database, craft the SQL in a way that it understands, and let it give you the answer that you want. That makes you more efficient, that makes your application less bug prone, that makes your application smaller, that allows you to get more work done. And I think these two topics really work well in that kind of vein. So being prepared as we go forward to say, oh, I didn't know I could do that, or oh, I've already done that in my application, now I don't need to do that anymore, I can rip out all that code and actually express it in SQL, give it to the database engine, let it give me the results that I want, make my life easier, right? The reason relational databases have been around so long is not because everyone likes to spell out the word between or select or what's some of the other really long ones. Some of the keywords are really long. Nobody likes that. But it is a very expressive language, and it's a declarative language, which I'll talk about in a minute, which allows the application developers to be very efficient. And that's really where you distinguish yourself as an application developer from someone who's just a grunt who's going to throw the database data into the database and pull it out and then go through all sorts of gymnastics in your application, and somebody who really uses that database for what it's good for and gets things done well, okay? And I think that is a real area that we're lacking, and I think these two talks are going to help with that, okay? So let's get started. So the first thing we're going to talk about is the concept of imperative versus declarative. That is sort of a general concept that I think is interesting. Then we'll talk about the syntax for common table expressions. Then we're going to kind of go sort of up the ramp, get harder, and we go to recursive common table expressions. This is where the SQL starts to be programmatic, or it allows you to sort of do things, push a lot of your work from the client application into the server. Okay, and then section 4 is where we kind of hit the cruise control, and we go through a whole bunch of examples using common table expressions, showing you how you can do a whole bunch of problems, again, using this feature. And then finally, section 5, writable common table expressions. This part is probably specific to Postgres, but it allows you, again, as an application programmer, to bundle a whole bunch of queries together and issue them as one statement. And I'll talk about why that's valuable, and again, I think you'll be impressed. Any questions? Great. Okay, first, imperative versus declarative, and we have a gentleman with a baton, kind of instructing the quartet here how to play the music. Imperative programming languages. These are languages you're probably familiar with C, Java, Perl, Python, JavaScript. These are languages where you tell the computer what to do. You are instructing the computer, conducting the computer, go do this loop, assign this value, here's this if statement, do this other thing, and you're telling the computer what to do. And this is the way most applications are written in imperative languages. And again, that's the methodology that you're normally thinking of as an application programmer. I need to do X, Y, Z. How do I get that done? Okay? However, SQL is not an imperative language. It's a declarative language. What is a declarative language? A declarative language is one where you tell the computer what you want, and the computer decides how to give you the answer in the most efficient way. Doesn't that sound great? All of a sudden, you're not having to go through every little if statement and every little conditional and, call your functions and all that other stuff. You're actually saying, I want this, you figure it out. And there's a whole bunch of reasons that's great, particularly because the system knows the data layout, the system knows how common certain constants are that you use in your query. I'm not going to get into that. I have an optimizer talk that explains that. But the server, the database server, knows a whole lot more about the data than your application does. And it is able, in many cases, to give you your results much faster than if you took a baton out and tried to instruct what you want the server to do. And that is why SQL is so powerful. That's why it's been around for so many years. And that's why it probably is going to be around for another 30 years, or 40 years, or 50 years at this point? 40 years. Okay. So this is typical imperative language. The first example is in BASIC. I'm showing my age here. That's what we used to do. If you ever run a program that just says hello over and over again, that's what that does. There's an example in C. There's an example in Perl. You're actually telling the computer what to do. In this case, say hello over and over again. Okay. This is a declarative language where you're just saying, give me hello, and then give me another hello, and so forth. It's not easy to do an infinite loop like I could in simple SQL, but common table expressions make that possible. I'll be showing you that in a minute. So just be aware. Imperative languages, typically applications are written in imperative languages. Okay, client applications typically use imperative languages. Server-side programming, typically done imperative languages. But, and the one place that you can do imperative languages in a database is using common table expressions. The reason common table expressions are a new way of doing SQL is because it takes a declarative language, which is SQL, and it gives you an imperative way of controlling it. So imperative is not bad. It's just that a lot of cases declarative is easier for you as an application developer. There are a bunch of cases where you need to imperatively control that database. And that's what common table expressions give you. It's a way of almost taking SQL and programming it similar to how you'd program in a language. And I will show you a whole bunch of examples where it is actually tremendously powerful to be able to imperatively control SQL, which by its nature, normally, by default, is a declarative language. Any questions? Okay, great. Let's look at the syntax. This is the common table expression syntax. Looks very simple. Effectively, the word that always starts a common table expression is the word with. So the word with basically indicates I'm about to start a common table expression. Then you have an optional keyword called recursive. I'll talk about what that means in a minute. Okay. And then we have an optional query name. And we have a query name we have to supply. Then we have an optional column name over here, right here. Then we have the word as. And then we have effectively a select inside this common table expression. I realize it doesn't make sense now. Give me a minute. I'll show you some really good examples. And then once you're done all that with stuff, there's a final select down here which says, here is my main query. So every common table expression you're ever going to see, always going to start with the keyword with. It's going to have multiple, one or more sub-queries or sub-selects or sub-queries, I don't want to use the word sub-select, with selects inside, and then there's always going to be one at the end. We're going to call that the main one. So you're going to have some ones at the top, and then you're going to have a main one at the bottom. That's always the structure you're going to have. Okay? Any questions? Okay. This slide. These queries are very complicated. So keep your eye on the red parts. If you see a query and you're like, where should I be looking? Look for the red part. Okay, that's what that slide's for. Okay, so here we got red part right there. See? So now all of a sudden you see it, you're like, oh, that's where I want to look. I want to look at that red part. Okay. So here is our first SQL common table expression. Right? Starts with the word with. Remember I told you that. It has a query inside the with, and then it has a main query here at the end. Right? Follows our syntax. or keyword with. It has one or more of these selects inside here, and then a main query at the end. Okay? Now, what can we learn from this? Well, first off, we've named this as source. In fact, this common table expression right here is called source. And in fact, I'm referencing the same name down here in my main select query. And this is a pattern you're going to see over and over again. Okay? You have a common table expression, you give it a name, and then in your main query, you reference that name. Now, this is a completely contrived example. You would never do this, but it is helpful to see what it does. You have select one is my subquery. Okay, so a row with one. It's called source, and my main query, what is it doing? It's saying select source. And what do I get out? One, because that's indeed what my subquery said. If I had a 2 here, a 2 would come out there. Okay? Again, we're going to start really slow, and then we're going to work up. So don't think this is a baby class, because by the time you get done, you're going to be like, your brain's going to explode, right? But right now, we got to start slow so we can get up to the complicated parts. And the window function's the same way. First 30 slides, you're going to be like, wow, we ever going to get anything useful? And then all of a sudden, it starts to be like, whoa, where did that come from? And then at the end, you're like, wow, that was crazy. I've heard that many times. In fact, a lot of people said that we thought we knew these features until we saw these talk, and we're like, okay, now we know it. You thought you knew it before. Another thing I should point out is that this talk and the window function talk were both written first as SQL. So what I did is I wrote the SQL I wanted to show, I ran it, and then I copied it into the presentation. So this URL right here is actually the SQL from this presentation. So if you download that SQL and just run it in PSQL or in pJadmin, you'll see the whole presentation fly by on your screen. Okay, just hit the pause button, but that's the entire presentation right there. And again, if you go to my website, you download the slides, you just need to click on that. It's everything in pink. You click on it, it opens a browser to that URL. Okay, so you don't even need to copy it. Just click on it in the PDF. All right. Any questions? Okay. Okay, here's a new one. So, same structure, starts with has the outer query of select, uses the same name, but what I did here was I labeled the column. Do you remember, I'm going to go back to the previous slide. You see how this has this weird parenthesis, like unknown column thing? It's like, hey, you didn't give a label, so I'm just going to give it this question mark, okay? But over here, I actually named the label, so now when I do it, I actually get a label here, and I can actually reference source.col1, and in fact gives me the thing. I can't do that here. I can't reference the column name because I didn't give it one here. So I just get this amorphous question mark or something. Okay. But again, this is normally the way you would do it. You'd label your columns so you can reference them in that main query. All right. Here's a new one. Instead of using the label here, I put it up here. You might remember that from the syntax. So instead of putting the label in the select, I put the label in the common table expression. Either way, doesn't matter. I get the same result, right? Make sense? Okay. Third one. This one we're gonna basically floor it. We're gonna push every label feature we can. Okay, so we're going to label it as col1 in the query inside the common table expression. We're going to make the common table expression call it col2, and then in the outer query, we're going to call it col3. Notice I had to call it col2 here because I had to reference this one, and then it actually comes out as col3. Okay, so I'm going from col1, col2, col3, same data. I'm just labeling it 3 different times. All right. So this is I think this is illustrative of what you do. Again, we start really slow, okay? But we're gonna get to some really crazy stuff. If you don't see crazy stuff by the end, I want you to tell me. Now we can do more than one column. We can do select 1, 2, and now we get 2 columns, right? We're not limited to 1 column. We can do 2 columns just fine. All right. Any questions so far? Good. Okay, I know, it's slow. We'll get there. Okay. I want to give you a little refresher on union because union ends up being used quite a bit with common table expressions. You'll see why in a couple minutes, but union is kind of our glue to kind of bind some of this stuff together, all right? Union's been around for a long time. Again, just added, it just was very convenient to be used with common table expressions, okay? And what I want to remind you is the handling of union. And I think this is sort of a unfortunate but probably logical behavior. But when you use union on its own, it will automatically remove any duplicates. And I'm sure the SQL Standard Committee has wonderful reasons for this, but it is kind of annoying. Here I'm selecting 1, 1, and I only get 1 out. If you use union all, you don't get the duplicate. So just a reminder, if you ever use union, the first thing after you type the word union, this is the way I do it. Every time I type the word union, I have to think, do I want duplicates or not? And the big complaint I've heard is normally in SQL, you add keywords to add features. Here you have to add keywords to remove functionality. You have to add the keyword all to remove duplicate removal, which is not super logical. I understand the SQL why they did it that way, but practically it becomes an issue. So just be aware of that. Union all, in most cases when I'm writing SQL, I want union all. And when I was an application developer, I remember 1 or 2 times when I'd be called in and they'd say, this report's not showing the right number, and I'd be like, okay, I'll look at it, and I'll come back like, 2 hours later, and I'm like, I'm sorry, we had 2 customers, they had the same amount, and the dupes got removed, and then when I do the sum, it came out wrong, right? Imagine, because you have 2 counts, the same, so anyway, be aware, union all is something you often want to do. Oh, so here's a new one. Now, I mentioned that you can have more than one common table expression, and this is our first example of that. So we now have a select that returns 1, 2, and we have a second select that returns 3, 4. The first one is called source, just like the previous one. This one is called source 2, okay? So we have select star from source, union all. I didn't really need the all here, but I just did it because I didn't want duplicate removal, more of a note to myself. And I say select star from source 2, and I have 1, 2, and 3, 4. Okay? So I've taken 2 common table expressions, pasted them together with union all, basically. All right? I can use common table expressions with actual tables, because I've used constants up to this point. So here I'm saying select language name, language role from PG language, and I'm doing a join here, okay? And then I say select star from source, and I get internals, and basically this is completely useless. I'm taking a query, and I'm giving it a name, and then I'm just selecting the data, right? Not doing anything, but hey, it's a good illustration. This is the first one that actually does something with common table expressions. Praise God. We have a query here. We call it source. We're doing our join. We're getting the language names. I'm saying select star from source, union all. I need union all here, the all part. Select min language name null from source. So the first 4 rows are these, okay, ordered by language name, and then I have an additional row that I didn't have before. All right. I don't think you'd ever want to do this, but if you did, this would make sense, right? You can kind of see I got my query. Your query could be huge. This is just a baby query. I could have a huge query, and now I can do like different analytics on it and return different rows that have different types of data in it. And I'm only running this query once. That's one of the key things, is the way Postgres implements this. That top query is fully run before we do the bottom part. Okay? So if you've ever had a case where you have to take a big query and run it one way to get one type of answer, another way to get a different type of answer, this is your solution. Put that big query in a common table expression, and then you can do all sorts of manipulation with it on your own. Okay? Okay. Here's another one. Here is a select from PG class. And now I am actually calling it class, and now I'm going to join this result 2PG attribute and then return 5 results, whatever. Okay? But here's the first case where I'm actually joining to a common table expression as though that common table expression was a real table, even though it isn't. Okay? We're good? Great. Questions? Okay. Another refresher. Case statement. I'm not sure how many of you have used case statements before, but a case statement is basically a conditional that you use in SQL. So, for example, this case statement right here is going to print positive, 0, or negative depending on the value of col. Now, this is a stupid example, but again, it's like an if statement for you. Yes, sir.
Can you go back one slide?
Yes, sir.
You have a limit 5 there.
Yes, sir.
You said earlier that the with plot executes completely from start. So if you had a million rows, it would return a million rows.
Yeah, so this is an excellent question by this gentleman. He's saying, we have a limit 5 down here, but we don't have any limits up here. So how would you actually have to execute this entire query, instantiate it in memory or spill a disk, and then do the join down here? And the answer is yes. The common table expression is what we call an optimization barrier. That is actually good in some cases and bad in other cases. There's some reasons why we have to make an optimization barrier for some of the later features we have. We've talked about removing that optimization barrier, which would allow the query to move around. We haven't implemented that yet, but I think one day we will. We've debated a couple times, and I think we're getting closer to doing that. But the idea of an optimization barrier in this case is what the problem is. And in fact, the operational problem is you do not know, well, I know they're all going to join, right? No, actually, I don't know they're all going to join. Yeah, I do know they're all going to join. So I know they're all going to join. So effectively, I could probably move the limit up there as well, but if I didn't know they were all going to join, if I put limit 5 up there and only 4 of the rows joined, I only return 4. So yeah, this is a problem. Great problem. Another thing that actually people have asked about a lot is there any overhead to these common table expressions? Not really. If you realize they're an optimization barrier, there's really not a whole lot of downside to them. Same thing with window functions. There's really not a lot of performance impact or a reason you would avoid using them, except, again, because of the optimization barrier issue. And just be aware of that. Okay. Other questions? Yes, sir. So what is the difference between having a view versus a common table expression? Great question. And this is actually, we could illustrate it right here. If class was a view, we have well, let me back up. So queries in Postgres go through 4 stages: parser, rewriter, optimizer, executor. In the rewriter, the second stage, we take views and expand them into the places they're referenced. So what would effectively happen here is this query would get basically expanded like a macro right at that spot. And we would be able to optimize and remove and move around where clauses and stuff like that in this particular case. So I would definitely argue that view is going to be much, much better in terms of optimization. Great question. Than trying to do a common table expression here. Yeah. In fact, people often use common table expressions when they want the optimization barrier. They may want operationally that one query to run before the rest of the query. But if it's a case of just, I want to encapsulate this thing, you're better off using a view. Yeah, because in a view, we don't have the optimization barrier, and we can move around stuff, and we get much better query plans. Great question. Other questions? Okay. So again, back to this conditional here, the case statement. It's basically like an if statement, and you're going to see some examples of this. Okay. Okay. Any questions? Okay. I actually just added this slide. If anyone wants to explain why this slide is recursion during the break, or anyway, there's actually a reason why this is actually a perfect recursion example. Yes.
Would it be fair to say that the reason facilitate views might be better
So the question is, would we conclude that views are better only because we haven't yet used any complicated things? And the answer is no. In every case, a view is going to give the optimizer more opportunities to move things around. The reason where you're going to use, and again, what it is you haven't seen yet why this would be useful, right? And you're going to see that in these coming ones, right? But effectively, the reason the common table expression is useful is because it gives us that imperative control. And we're going to see from here on a whole bunch of cases where that imperative control is crucial to doing what we need to get done. Up until this point, you're absolutely right. There's been absolutely no reason to use common table expressions in any of the examples that I've given you. Thank you. Very good. Other questions? Great. Okay. Okay. So, recursive. Again, this is where we start going up the hill, as I said in the beginning. A recursive common table expression is one where you are potentially executing the SQL multiple times. You don't have to, but you're potentially executing the SQL multiple times. Now, in this case, you don't. I've added the keyword recursive here. You might remember it from the SQL syntax I showed you earlier. Remember that? Okay. So we have the keyword recursive, but effectively, it's the same query, right? We have select recursive source as 1, and we turn 1, right? Really not very powerful, okay? This is kind of where we start to go way up, okay? This is where we actually see a common table expression that effectively goes into an infinite loop. Now, I don't recommend you writing common table expressions that go into infinite loops. There's probably little value to that, okay? But you are going to see a whole bunch of cases where the ability to do looping in SQL in an imperative way becomes very powerful, okay? Okay. Is the mic working? Does everyone hear me back there? You're good? Okay, just checking. Thank you. The perfect mic is the one that I can't hear, right? I was just making sure everyone can hear clearly. Okay, so what I actually did here was I said set statement timeout equals 1 second, which is so it canceled itself, and I used with and I used the word recursive, and this is the structure we're going to see over and over again with recursion. There's this sense that you have to prime the recursion, okay? In this case, I'm selecting 1. That's my prime, to prime it. And then I have a union all. Again, I talked about union all before, to paste the second query that references my own common table expression name. This is where the recursion part comes in, right? So we have 1 becomes source. The second query returns 1. Another 1 goes up. 1, blah, blah. All of a sudden, we're in an infinite loop. Okay? This is effectively what's happening. You select 1, it goes into source. You select from source. You have another 1. It goes up, down, boop, 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 boop. I can't get out. Okay? And this is the pattern we're going to see over and over again. Here is another example. I am now displaying the word hello over and over again. Remember the example I showed you earlier with imperative, where you just said hello, 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 hello. Effectively, I have hello. I select source. Source says hello again. Hello, hello, hello. It doesn't stop. All right? Not very useful, but that structure we're going to see over and over again. Okay? This is interesting. This is interesting. It's exactly the same as this query, except for what? All. Thank you. See, the all disappear right here, and there it is, and it's gone. And hey, I labeled it in red, so everyone probably realized that's what was going on. And what's really interesting is the hello goes into source, the hello comes down, and when it realizes there's already a hello in there, nothing gets added, so it returns just one hello. Okay? An example of almost every case you're going to want to use union all in these recursive queries. Yes, sir? So in the different layers that I talked about, where does that optimization happen? It happens very quickly. So you're absolutely right. Does it generate an infinite number of hellos before it terminates, right? It's really your question. No, the parser does not catch it. What actually happens is the executor executes the hello. It then goes into source. It loops around again. It then takes the hello and it tries to insert the hello into the existing batch it's holding. Because remember, it normally thinks it's going to run and create like an in-memory or disk spilling copy of source, right? And because nothing gets added, it knows I don't need to come back here again, and it just exits. Great question. Other questions? Yes, sir. Oh, so you've been looking ahead at the slides. That's why I wanted to find out how to download the slides. Yes, you're absolutely right. This gentleman is right on it. There is no where clause here in this second part. Okay? And because there's no where clause, effectively it tries to go forever, and frankly, how would you get out of it? And the way you get out of it is a where clause. Okay? And here it is, right, in red even. This is a query that counts from 1 to 10. If you think of, imperative languages, when you learn imperative languages, print the numbers from 1 to 10, do a factorial, right? I mean, all this sort of academic business when you're learning a language. We're doing this now in SQL. In fact, I have a factorial example coming. So, we're going to go through CS 101 here. So we have select 1, which is what we call our seed value. Starts the counter, primes it. Okay? 1 goes up to the counter. Now I have select 1, and I check to see is 1 less than 10. Yes. I return 1 plus 1 is 2. And then I go back up here, 2, 3, 4, 5, 6. When 9 comes down, 9's less than 10, I return 10. 10 goes up. Is 10 less than 10? No. So I don't return anything here, and I exit that common table expression and pop down here to return the result. Okay? And that is the result, in fact. Now, we do have an easier way of doing this in Postgres generate series. Makes it very easy to go from 1 to 10, but you get the idea. Okay? And this is how you would do it in Perl. Again, for those of you who know Perl, it's just an example. We might have somebody who knows a lot about it here, maybe. Randolph would know, but anyway, we have a little example here for people, just so you have a framework of what we're doing. Okay. In fact, this example is not that accurate. This one is accurate. Okay, and I'm not sure he caught that or whatever. But in this case, you're going from 1 to 10, and you're not really queuing the results. You're printing them as you go. Okay. In this example, and I hope it's correct. Effectively, what you're doing is you're creating a function f, and then you're priming it with 1. Right? And the 1 is going up here, it's going into arg, it's printing the 1, and then it's calling the function again with 2, as long as it's less than 10, and then it goes around. Okay? And frankly, that one still is not right. This one is right. Okay? Because even here, I'm doing recursion. This one, I'm not doing any recursion. Right? This one, I'm doing recursion, but I'm printing the results as I get them. Right? And that's not the way common table expressions work. They don't feed the result down to the main query until they're finished. So this one is right. I basically create a function. I start it with 1. I push it into an array. Then I call it again. I do it to 10, and then I output the function, the array. So this is really the right example, because I am queuing up the values in memory into an array, and then at the end, in my outer query, I'm printing the array. Does everyone get that distinction? Right? I went from a simple for loop, which is really not what we're doing in SQL, to this, but again, this is outputting them as I generate them, which is also not accurate. This is the more correct example. Yes, sir. Well, I thought about making one passed in here, but it was kind of simpler to do it this way. So this construct in modern Perl basically says if I haven't passed anything in, which I haven't, use one. And I would argue that that actually is more accurate. Okay? We could probably spend quite a bit of time understanding which Perl is exactly more like common table expressions, but I think this one got really close. Any questions? In fact, just an aside, I was at a conference and somebody said, he said, I've looked at your presentations and it's as though you write them to be studied. He said, yeah, I guess because of the red and stuff. He said, I'll take it and I'll just go through it slide by slide. And I'm like, there's a whole story inside a single slide sometimes. And I think that's an example of this. So I used to be a high school professor and then did some college work, so I guess I'm used to that. But I also love it. So and I know we have a lot of teachers here as well, trainers. Other questions? Okay, examples. Again, I've shown you a lot of academic stuff, a lot of stuff that doesn't make a lot of sense. Now we're going to actually do some cool output stuff with this data. Okay, so factorial. I promised you, every time you learn a language, you got to learn how to do a factorial, right? And we're going to do that in SQL. I don't recommend you do it, but again, great example of showing how you take an imperative problem and you force SQL to do it. Now, Postgres has a factorial function. There's no reason to do this, but it's very illustrative of seeing how to do something. And we see all of the common features, all of the common structures of common table expressions here, right? Starts with, right, which we know. Uses the word recursive, which we know, right? Then has a source, and then it labels the two columns, counter and product. We start with 1, 1 as a prime, and the first column goes up by 1 each time. The second column takes the counter, adds 1 to it, and multiplies it by whatever the product was. All right? And we do it up to 10, and then at the bottom we just output what we have. And if we look at the output, that's exactly what we think. There's 10 factorial right there. Right? And we also have the factorial of all the numbers up to 10 as well. Now, you may not want that. You may only want to see 10. So what I effectively did here was I added a where clause in the outer to say, let's trim off all the other stuff that came from the common table expression. Just give me the 10 that I want. All right? And that's a very clean output right there. Yes, sir. So yes, you're correct. If I tried to do any filtering in the CTE, it's going to the effect of that filtering is to stop it from continuing. Okay. Now I did do filtering here. Now what I cannot do, and this might be where you're going, I can't have this where clause and get rid of that, because the problem would be I would never finish the common table expression to get to that where clause, and because there's an optimization barrier, I can't take the where and pop it up into the common table expression. Yeah. Well, yeah. In fact, because the counter wouldn't equal 10, because it started out as 1, it would just stop. Perfect. Yeah, that's a perfect example. Perfect example. And again, keep asking questions. This is a tutorial. This is what it's for. You chose not to have those breaks. Let's do the Q&A, right? I mean, there's a wealth of stuff here. When we do window functions, it's going to be a wealth of stuff. I guarantee you. Like, whoa, what in the world was that? So I'm used to that. Okay. Yeah. So the question is, without recursion, is there value to doing CTs instead of U's? The answer is there are performance values to using CTs instead of U's. Yeah, there actually are. And the reason is because there are some cases where you, as an application developer, know more about your data, or you have a particular query that uses a very expensive function, and you want that function to be run under your control, not over the way the optimizer happens to reorder your function call. Or certain joins you want done in a certain order, and then outside you want to do something else. So there are a number of developers who will take a long query and actually break it up into parts because they want to control the order. Now, we should probably add an option to turn that off, but my guess is we'll probably keep the optimization barrier there by default, particularly for that reason. Okay? Yeah. Other questions? Can you tune the optimizer so the CTs are not an optimization barrier? I think we need to add that feature. It's on the to-do list, but we have not done that. So you cannot tune the common table expressions not to act as an optimization barrier. I would like to see that happen, but it has not been done yet. Yeah. Other questions? Great. Okay. Let's see. So effectively on this, and this is actually the Perl example of what we've talked about. Again, here's the priming, here's the recursion right here, and we're pushing the array, and then we're outputting. Okay. Okay. Now you might have seen me do a lot with numbers. You might think, well, what can I do with strings? And the answer is you can do strings too. Okay. So here's an example. I'm priming it with an A, and then I'm concatenating an A. So I primed A into here, and then I say, as long as the string length is less than 10, give me another A. Append an A, append an A, append an A, and select the whole thing, and I get all these A's like that. Okay? Not really exciting, but it works. So you might say, well, I want to have a B next to an A and then a C. Well, if you kind of parse this big thing here, it's effectively taking the last letter and then getting the ASCII value and adding 1 to it and then converting it back to a character again and then and you get this. Okay, A, B, C, D, E, F, whatever. And there's some examples. You can imagine some use cases. You might want to do this for populating a table or something like code table or something like that. That's kind of cool. This one always gets people kind of laughing. This is actually always the demo people use for common table expressions. It actually gives you an ASCII Art. I start with -10 and I go to +10, and then I print a certain number of spaces and then an X and a certain number of spaces and an X, and I get that. Okay, so I'm drawing a big X. There, watch this. There you go, exactly, big X. Here's another one. This should show you a little better what happens. We go from -10 to 10, and we print 0 spaces for 10, 1 space for 9, 2 spaces, and then again this size gets smaller. And here we're printing, I think, 8 spaces or 9 spaces, and then 2 letters next to each other. Right here it's 0, and then all the way down. Okay. You can do other things. I can make like a diamond by changing the way I'm computing this. So now it's a diamond. I can make it more rounded if I want. Use a little power there. I got like I don't know what that is. It actually looks like a piece of bread. Everyone sees like Italian bread like that. Hachapuri, if anybody knows Georgian food, that's what I used in Russia. Everyone laughed at that in Russia. But there are some breads that look that shape. And then I can do kind of this. This is more like a hachapuri to me, a little wider. Not really a great circle, but it's the best I could do. Okay. And I've seen ones where you do Mandelbrats, Christmas trees. I mean, there's a whole bunch of stuff you can do. I don't think it's very useful, but it's very illustrative, I think, of that imperative aspect. Okay. Here's another one. Again, usually a CS 101 example. Prime factors. So every integer has a certain number of prime factors. For example, for 100, it's 2, 2, and 5, 5. 66, 2, 3, and 11. And you can actually do this prime factorization in SQL using case statements, okay, as I told about before. Here's the prime factors of 56, and I basically run through, and I go from 1 to, this is my counter, this is my remainder, and this is whether it's a factor or not. And again, I do it until the factor is 1, and it basically for 56, I go down, and all of these that are true are factors. So 2, 2, 2, and 7 are the prime factors of 56. In fact, if I actually change my output and I say, only show me the rows that are prime factors, this comes up a little better now, 2, 2, 2, and 7, all my prime factors right here. Okay? Kind of cool. Yes, sir? Yes, the question is, does it execute this modular 3 times? Indeed it does, yes. Okay. Now, here's the prime factors. I just picked a number, 3, 2, 2, 4, 3, 4, right? And if I run it, these are the prime factors of that number, right? Very imperative. This is actually the prime factors of 66. And again, what you're noticing here is it's trying every number. Like, why is it doing 9 if it already did 3? Like kind of weird. Or like, why is it doing 8? You know, why is it bothering to do numbers it already did? So we can actually optimize this, of course. Make it faster. Here we only do the odd numbers after 2. Okay, and now that trims down quite a bit of the examples we have. It has an exit case there. Okay, and if, again, if we only want to see the primes of 66, there's the answer. Okay. This is, again, the example in Perl for that. Okay. Questions? Okay. So now we're going to get into Okay. So now we're going to get into an actual application that kind of you might do as a real person, right? Which is always a good idea. Here, basically, what we have created is a part table. And what we're doing is we're inserting a whole bunch of parts. Now, the interesting thing about this part table is that it has parts and then it has subparts. So think of an airplane. What does an airplane have? It has fuselage, wings, wheels, tail section, right? But then inside the wing, there's a whole bunch of parts. Inside the fuselage, there's a bunch of parts. The wheel has a bunch of parts. The landing gear, the tail thing, right? So effectively, for each we have a number of parts like part 1, but then we have subparts for part 1, and then part 2, and subparts for part 2. And then part 11 has some subparts, and part 13 has some subparts, 22 has some subparts, and 23 has a subpart. So think of this as a tree, okay? And the use of sort of tree traversal in SQL is very common for common table expressions. Without common table expressions, if you need to traverse a tree, you have to effectively call the you have to issue a query. Give me the top level parts, and then for each top level part, you then have to send a query again. Give me all the subparts of the fuselage, and then for all those subparts, give me all the subparts of the fuselage, right? And you have to keep going down, down, down. You're issuing queries over and over again from the client, over and over again. What common table expressions do is they give you an ability to do all of that tree walking in SQL. Again, that imperative aspect where you're telling it, walk the tree of the parts, walk the tree of the plane, and do certain behaviors. Okay. So this is how we prime it up. Here is a recursive common table expression. We're saying for part 2, which is this set right here, give me all of the subparts that are parts. So if this is the fuselage, part 2 is the fuselage, 21 and 22 are 23 are subparts, and then these are subparts of the fuselage. Okay? Now, you might not like that, but I mean, this is a very simple example. All we're doing here is we're priming it with 2. We're saying, join the source table part number and give me all the subparts, and then return that to up here and then keep going. So that's how your loop is going here, like that. Okay, walking down. Yes.
So that's really interesting. So that means that each iteration it can get more than one result that it's doing. So I'm guessing it only gets the result that hasn't already been returned in the previous iteration.
So that is a great point. Um, this is one of the first cases where the subquery here is returning more than one row. Because up until this point, we've always had it returning one row and 1 to 10 or whatever, right? Now our subquery or this query here could return multiple rows, and in fact that means that this 3 rows get added there, and then 3 rows get instantiated. Now it's a 3-row table instead of being a 1-row table, and it's going to roll through. Now, because of the way this structure is set up, I don't have any loops. So I'm never going to loop around and end up back where I started from, okay? Because that would be bad, right? And you can't say that the wheel is part of the fuselage, which is part of the wheel. Like, it doesn't work that way. Nobody would set up a plane like that because it would never fly, right? But one interesting use case, and I normally don't cover this, but I've been sort of harping on the fact that we want to use union all in almost every case. Now, if you're worried that your data has loops in it, okay, this is an excellent, and maybe I'll add a little mention down here now that you picked that up. Nobody picked that up before. Maybe if you're worried that your thing has loops in it and you're willing to have the overhead of the duplicate removal, okay, you may want to remove the all here. And what that will do is prevent it from going into a loop, just like back on slide 20-something when we did the hello and we didn't use union all, it didn't loop. Do you remember that? Because it knew I already had one hello, I'm not going to add another one. So if you're worried your data has loops, you might want to remove that union all there. Right? Yes?
So then would it stop when it hit the first loop, or would any other rows?
So all it's going to do is just going to remove the rows that were duplicate. Any other unique rows are still going to be fed in. Okay? It's not going to stop on one. It's going to say, oh, I have 3 rows. One of them is duplicate. Now I'm only going to pass 2 rows up and loop on those 2 additional rows. Yeah. Yeah. Yes, ma'am. Great. Thank you. Yes, sir. So you're asking if you can add a limit 1 here, out here? I'm sorry. Here? The problem, if you add a limit 1 here, you're only going to get the first part of the subparts. So if you may have an example, this would be a great example. So if you added an order by here, and you said, I want to see the closest friend of this guy, and then I want to see the closest friend of that guy, of his friend, you would eliminate all of the secondary friends and only get the primary friend if you could have a ranking of friendship for the guy or woman. I don't know. I guess there might be some cases where you would not want to fully go through the whole hierarchy of sub-objects and just pick one. But you'd have to have an order by in there. And what I don't remember is that the order by is executed for each iteration or only at the end. I think it's each iteration, but I have to look at that. Nobody's ever asked me that question. But normally you're going to want to use probably not limit unless you're sure. And you're probably always going to want to use union all, again, unless you have loops in there and then you want to eliminate the loops, and that would be a good way of doing it. Yep. Yes, sir, in the back. Can you be a little more specific? You used some acronyms I didn't know. Yeah. Yeah. Okay. So that's interesting, and I'm going to have to go here to kind of talk about that. So if I was returning the parent of these objects, then the union all would get me into an infinite loop. So one of the reasons that I'm just returning the subpart that goes with the part is if I returned the parent would keep repeating, and I'd never get out of the loop. So I think anytime you're going to get duplicates, unless you get rid of that all, you're never going to get out of that query. But there might be cases where you'd want to stop at a duplicate, and that's where you would use the get rid of the all, basically. So if you have a child node that has no parent, multiple parents. Oh. So so if you have a child with multiple parents, so that means you have multiple ways of going in, and in that case you probably would remove the all, because then you would get rid of, that's another example I hadn't thought about, but you're right. You would have it. Your child may appear multiple times, and if you got rid of the all, it would only appear once. That's right. Now there's another trick to this. And the trick is that I'm only returning the part number. I might want to return the parent to go with it. And I'm going to show you some examples in a minute, which really go a little bit onto the steroids kind of range. Because right now I'm just returning a number, but wait till I show you a little bit more here, okay? So this, I'm just returning the part number, right, straight. And again, it doesn't handle the case where a child might be part. You might have the same part in the fuselage and the wing, right? The same bolt might be used in both places. So that's a good example. So in this case, I'm actually returning the level with the part, okay? So here now I'm actually putting a level, and I'm having a different number of dashes depending on what level it's at. So now I'm displaying graphically how far down this subpart is, all right, using this part in red here. And I can also order it, so now instead of having the part and the subparts, notice these two parts are parent of this one, and this one's parent, but they're all kind of bunched together because of the way I've ordered it, okay? So now I'm going to order it by the tree, and the tree is effectively a concatenation of all of the part numbers, okay? So now I'm getting not just the part, and gentlemen, you should take a look at this. Now I'm not returning just the part, I'm returning the whole hierarchy of the part. And that's where I start to get rid of I don't have duplicates, because if the same bolt appears in two places, they have different parents, different tree hierarchy, right? So effectively what I'm doing is I'm now giving the tree hierarchy to come down. But this is kind of weird because I'm actually doing it as text, which is kind of awkward. So in this case, I'm actually creating a Postgres array, and I'm appending the parts to the array, and now I'm getting a nice array that I can order by. So instead of doing the ordering by ASCII, which is really terrible, don't do that, right? Because again, it's just not going to work the way you want it to. Like, what is it? 9 is going to appear after 11, because 11 is ASCII less than 9. You get, right? So by doing it this way, I get everything in an array, and then I get a graphic. So in a lot of cases, you wouldn't want just the part. You'd want to see the whole hierarchy like that. And now if we have a part that appears in two places, it's going to appear two different times, even though we use union all, right? And we're going to get a clear, this part appears here, and this part also appears in this hierarchy. All right? And the full output is basically this. You can see it, the different levels, the different part numbers, and then the tree, and then the array that gives me the structure of all that. So again, this is kind of taking that part, building more and more and more until we're starting to do some really useful stuff. Again, not having to repeatedly send queries over and over to the server. We're actually just sending one query. The server's doing all the work, much more efficiently than we could do, and then returning the result back to us. Okay? I think very, very powerful. Any questions? Got that example. Okay. Postgres has a dependency table inside, built in. So I'm just going to show you an example of displaying the Postgres dependency table. This is an internal table that's only used by Postgres. You'd never use it yourself, probably. But here, if I create a table called dep test, I can actually look at the Postgres dependency table, and I can actually output the dependencies that come from that new table I created. And if I add if I don't want to see depth, these are the dependencies without seeing the major one. Now if I add a primary key to the table, I now have 2 new dependencies, right, from my table. And if I add a serial column, I now have 4 new dependencies, okay? And again, you can see how internally Postgres has this dependency table. One table has a couple like 6, 8 dependencies, and again, I can walk that hierarchy within this complicated SQL query. This is very Postgres specific. Again, you would never use this probably, but the idea of creating a dependency graph in SQL, obviously very possible and very easy to access using common table expressions. Okay. And effectively, this is the tree right here with arrays of object IDs. You can see some of them are primary, some of them are sub-objects, some of them are sub-sub-objects. And again, we could go down as far as we wanted. Questions? Okay. So we're getting to the sort of end where I promised that you would be confused or at least surprised. What we're going to do is we're going to conclude with writable common table expressions. Again, this is Postgres specific as far as I know, but it does take common table expressions to a whole new level in terms of what they can do. Okay, and once we're done this section, once we're done this slide, we'll take a 20-minute break, go out, have something to drink, or just stand up and walk around. And of course, when we come back, we'll do window functions, and hopefully your brain will have relaxed by then, because the window function talk is, again, very complicated. So you will need that break to sort of let your brain unwind a little bit. At least I always do. Any questions before we get started? Okay, great. Okay, so writable common table expressions. Writable common table expressions. So these 2 bullets are not the same thing. I will try and highlight the difference. Writable common table expressions allow data modification commands in the with clause. So you've normally seen only selects with common table expressions, right? But what we're going to show you now is cases where you do insert, update, delete in the with query, okay? With a select at the bottom. So the main query is a select, but inside that common table expression is an insert, update, delete with a returning clause, which I'll tell you about in a minute, okay? That's bullet 1. Bullet 2, allow with clauses to be attached to insert, update, delete statements. In this case, the query inside the common table expression is a select, and the main query at the bottom is an insert, update, delete. Okay, so 2 examples. One has the insert, update, delete in the with query. The second example has the insert, update, delete in the outer query, that's the bottom query. Does that make sense to everyone, that distinction? Okay. First example, we're going to create a table called retDemo. I don't know why I call it that. Return demo, I guess. And we're going to insert 3 random numbers. But we're also going to use a special Postgres syntax called returning. This is not SQL standard, I think. David, can you confirm that's not a? I think it's a Postgres baby there. Yeah, it kind of takes this stuff to the next level. So, for example, if you're inserting 3 random numbers, you really don't know what those random numbers are. But if you do a returning clause at the end, you can actually get the results back from the insert. All right? Kind of cool. Here's our first example. Inside the common table expression, I'm doing an insert of 3 random values, and I am using the returning clause. What does the returning clause behave as? It really behaves like a select. Right? Doesn't that look like a select output to you? Right? So it's an insert with a select kind of at the end, which only returns the rows that I inserted. Kind of cool. So here I can say, insert 3 random values, return as a select, and then give me the average of those 3 inserted values. Kind of cool. Okay? So, 3 random values, give me the average. There we go. Here is another example. Delete all of the rows in the common table expression. Give me all the rows in the table, but return a select of all the deleted rows, and give me the maximum one. What is also very interesting about this is this happens as a single snapshot, as a single transaction. So this would be very hard to do in another example because you would not be sure you got all the rows. Like somebody could have inserted a row between your delete and then you're like doing some weird stuff. You with me? Okay? So the delete happens in the same snapshot. I'm returning all the rows and then that result's coming right back and I'm doing the calculation. There's no way to get in the middle. No way for somebody to get in the middle there. There's literally no way to do this unless you, I guess, lock the table and then in a transaction block, delete it, select it, delete it, and then give the like kind of awkwardness, right? Whereas this is like, bam, one query. Yes? So is this whole thing atomic if one of these was to die or fail? It's completely atomic. It is one block. Now, if you're doing this inside a transaction block, then again, it's a single query, and again, it's controlled by. It could abort the whole query. You could have a save point in there, whatever. This is one single query. If you're not using a transaction block, then effectively it's its own transaction. Yeah. Could you use that to move from one table to another? Absolutely, you can use it to move from one table to another in an atomic way. That's right. And what you could do is you could delete it. This is exactly where you're going. You delete it and then insert it, right? And I have an example right. I'm getting to it. I will show you an example. Okay. So this is the second bullet. This is the case where we do a select inside the common table expression, and then we do an insert, update, delete outside. So here I'm going to do another table called vetdemo2, and I'm going to insert 3 random numbers. I just seem to love random numbers. And here I say with source, give me the average of my rows in vetdemo2, and then delete everything less than the average. Very, very hard to do in normal SQL unless you lock the table, right? And, and then do your operations, right? This is one query. So we're basically saying, give me the value, and then I actually, now I can look and see how many rows are left. In fact, because I deleted all the lowest values, I only have 1 row left. Yes, sir? Where am I? What's the transaction? Where am I committing the transaction? Postgres is in auto-commit mode, so by default, every query is its own transaction that's committed when it finishes. It is not like Oracle, which is not in auto-commit mode. You have to commit after every command unless you turn that off, right? In Postgres, the default is to be in auto-commit mode. You can turn that off, but by default, it's in auto-commit mode. Okay? Oh, so the question is insert the data manipulation language. Postgres effectively, that entire query is one transaction. Whether you do insert or delete, I'm going to show you an example in a minute that does an insert and then a delete and then another insert. That is one query. That is one transaction block. If you're in auto commit mode, you don't even have. You can even put DDL in a transaction block in Postgres, whereas Oracle, yeah, it just goes crazy. So again, we're getting on to steroids here, but we've had this for 20 years. We've always allowed DDL in transaction blocks, certainly DML, multiple DML. In fact, DML pasted together with common table expressions, which is what we're going to show you in a minute. I haven't even gotten to the most complicated one yet. Okay? Yes, sir. So yes, it does. So this is auto-committed, this is auto-committed, this is auto-committed, and that is auto-committed. Thank you. Thank you. Very good point. Very good point. Thank you. Other questions? Okay. Okay, so here's another cool one. Basically, I'm saying take part 2, generate all the subparts, and then delete them all. Right? Great use of a common table expression that does a recursive select and then deletes everything it returns. One thing this does not do, and I need to go back to this gentleman, if you had a subpart that was used in 2 places, I'm afraid it would delete it, which is not good. If you had a subpart that was used in 2 places and you didn't delete one of them, the other one would delete, the whole thing would go away. That's a problem, yeah. So maybe that's something we should work on. But again, this is a tutorial, if it's good, that's something I really hadn't thought of. You started talking about having a part in 2 places, and then I started to think, oh, yeah, that would be a problem. Other questions? Okay. So again, great example. Walk a tree, delete a tree. Remember, we did walk a tree, return a tree. Now we'll walk a tree, delete a tree. Really, really very convenient. Here's where we can start to go, woohoo! So here I have a ret demo 3. Again, as I told you, I have the SQL. If you want to run it, you can run the whole SQL command, fly it off your screen. Ret demo 3, put 3 random numbers in, okay? Give me the average of the 3 numbers in the table. In the second common table expression, delete all the rows that are less than the average, and then return what's deleted. I could also add it to return what's left if I wanted to, but I did just what deleted, right? So we're saying, give me the average, delete everything less than the average, show me what I just deleted. Yes, sir. One slide. Okay, so here we start to go, this is actually, I think, really useful, frankly. Here we have an orders table, which has an items table, right? So standard, you have orders, and each order has a bunch of items in it, right? So classic case. So I have an orders table, I have an items table. Now I can say insert into the orders table, but you might notice that this is a serial column, so therefore it's auto-numbered, okay? And I'm using the default, which says insert in the orders table, and then give me the default order number. So assign the default order number during this insert. This is the way it normally works, right? Normally you then have to find the order number with next val or last val, per val, and then use it that way. But what you can actually do is you can say return the serial column I just assigned, and then insert my order using the same order I just used. So what I've done is I've inserted in the orders table and the items table in one statement, right? Instead of having to do the query and then say give me curval and insert curval up, I'm doing it together. Okay. Here's another one: delete from the orders table, return the order ID, and then delete all the items for those orders. So again, just like that delete the orders, and then as the same thing, delete the items for the orders. And you can see how you start to combine stuff together becomes very, very powerful. Okay? Okay. Here is another one. Delete from the orders table, then delete from the items table, and then take the order number and insert it into another table, like as a backup. So I've got an old, I have an old orders table, and I want to just say this is when I deleted it. And probably I'd probably add like a curval here, or like current timestamp, so I know when I deleted it. But again, this is just an example, right? But that's how you would effectively do it. If you wanted to move data, which the gentleman was asking about, right, you would delete, and then you would insert into the other table. And in one snapshot, in one visibility, right, you'd move the rows from the one, you'd be deleting them, they'd be returned, and then you'd be inserting them somewhere else, and then committed together. You can't lose any data. There's no visibility. You don't even have to lock the thing. That's the beauty of this. Normally, to do this, you have to lock the table, select it, delete it, insert it, and then delete it. And while you're doing that, the stuff's locked. Here, you're locking each row as you're deleting it, but you're not deleting. You're allowing other inserts to happen to the table at the same time. Right? So it's kind of like I'm moving stuff around, but at the same time, people can be adding new rows that aren't part of my snapshot. I don't see them. I don't delete them. Nothing happens. Right? Tremendously powerful. This is not only making your life simpler in terms of having one query that does a bunch of things, but it's allowing you to do something concurrently that's very hard to do any other way. Okay. So, why use common table expressions? We're almost done. Allows imperative processing of SQL. Merges multiple SQL queries and their connected application logic together. Unifies them. Okay. Improves performance by issuing fewer queries, less transmission overhead, less overhead for optimizing, for example. Uses the same snapshot for the entire query. Very hard to do this outside of common table expressions. To have multiple queries use the same snapshot. You can use repeatable read mode. That kind of gets you around some of that, but then you still have to lock the table, which you probably don't want to do. But it does add an optimization barrier. Okay? And that is all I wanted to cover today for common table expressions. So what we're going to do is it is exactly 3 o'clock. Is that right? Yes? And what we will do is we will break until 3:20, and we will come back and we will talk about window functions. So 20 minutes. Have a good time. Just a reminder, we will start promptly at 3:20, so. We'll get started in a minute. We'll get started in a minute. Okay. Thank you. Welcome back, everyone. I won't need to go through introductions again because we did that. Same story. Presentations are on my website. Bruce Momjian, work for Enterprise DB. One thing I will tell you about this talk is that Postgres implemented window functions 6 or 7 years ago. And at that time, I thought, hey, this would be a great talk. Let me write a talk about window functions. And I started writing a talk, and I got stuck. And I kept the SQL around. Again, as I said before, I write the SQL, and then I write this talk. And this summer, I got a chance to go back to this topic, and for some reason, it gelled in my head, and I was able to write the talk. So some parts of this is 6 years old. And the reason I got stuck is because there are some aspects of window functions that are just really hard to get your head around. So the first part of this talk will be getting your head around some concepts and some terminology. So as we get into some actual use cases, it will start to make sense. Okay? So again, this should be about 1:10. Take us to 4:30, finish up. I will be around, of course, to answer any questions or help anyone. After that, I might go to 4:35. I might need an extra 5 minutes. We shall see. Any questions? Okay, so what are we going to talk about? First, we're going to introduce window functions, what they are conceptually. Then we'll talk about the syntax of window functions, very similar layout that we had with common table expressions. Then we'll look at the window syntax with generic aggregates. They may not make sense to you, but these are things like sum and count, average. Then we'll talk about window-specific functions, things like lag, lead, rank. And then in section 5, it really gets interesting where we take a real-world example and do analytics on a particular table with a certain number of employees. And finally, we'll finish with discussing considerations of window functions. Okay? Okay, so introduction to window functions. What are window functions? Window functions are part of a larger set of features that Postgres supplies for data analytics. Things like data partitioning, materialized views, common table expressions right there. That's something you can use for data analytics. Print index, grouping set, roll-up, optimize aggregates, table spaces, all things you would use for data analytics. Window functions is merely an additional feature that people use for data analytics. And again, follows the same pattern we did before, the concept that using window functions makes your life easier. As application programmers, having window functions and not having to reinvent the wheel and giving the database server the problem and letting it solve it is often the best and most efficient approach when you need something done. And that's, again, sort of the policy we've come through this entire thing. Okay. So what are window functions? This is a section from the Postgres documentation, slightly modified by me and committed to probably 6 or 9 months ago. So this is what the Postgres 10 docs look like. Effectively, just to highlight some words here, normally an aggregate will reduce or aggregate a number of rows into a single row. However, window functions do not cause rows to become grouped into a single output row like non-window aggregate functions would. Instead, the rows retain separate identities. Okay? Behind the scenes, the window functions can access more than one row. Okay? So when you think of running an aggregate, you think of taking a whole bunch of rows and getting a number out of it. In window functions, the rows retain their distinct characteristics. You do not eliminate rows when you're using window functions. And that is perhaps the fundamental difference between normal aggregate and a window function aggregate. I know it doesn't make a lot of sense right now. There's a whole bunch of stuff I'm going to talk about in the next 10 minutes or 15 minutes that doesn't make any sense. But they will make sense by the time we're done the talk. Because I'll be talking about concepts that you think would have nothing to do with window functions, but in fact are fundamental to understanding them. As I said earlier, a lot of people have seen this talk, have used window functions before, say, oh, I thought I understood them. Now I really do understand them. In addition, there's a lot of people who, when they need to do a window function, just do a web search, find a window function that kind of does what they need to do, whack it around, and hope it works. That works some of the times. There are some pitfalls to that. So I believe if you're going to use window functions, don't sort of put it on autopilot. You should understand what you're doing with these words you're typing, and that's really the goal of this talk. Okay. Any questions? Again, keep your eye on the red, because we're going to use the same pattern of looking for red text within the screen. Okay. So here is a query I'm going to use repeatedly in the first part of the section. The function called generate series, which effectively just generates the numbers from 1 to 10. In addition, just like the common table expression talk, we have a window.sql file, which is this entire talk as an SQL file that you can run in your browser or in PSQL. Okay? Yeah. Yes, this here? Yeah. So when you call a function inside of a from clause in Postgres, you need to label the name of the virtual table and the name of the column in that table. You could kind of guess that the function would be called the table would be called generate series. But it's not really clear what to call the column. So we kind of require you, and this SQL standard kind of requires you to actually label what that function's name is for the virtual table and the name of the columns. You could have more than one column. Other questions? Okay. So here's our first window function. Wow. We got the window functions on slide 8, right? Why do I know it's a window function? Because of the word over. Anytime you use the word over, you're now taking an aggregate and making it act as a window function. Just what it is. That's what over does. Okay? There also is an optional frame clause and other clauses you can put in parentheses. In this case, we don't have any. So we're just going to use the default. And when you actually look at the result, it's really confounding. Like, this is the best we could do, and indeed, it's not the best we can do, but that's the default behavior. The default behavior for a sum with nothing in the parentheses is basically to sum the entire set and place on every single row. One of the aspects that you need to realize here is we have not reduced the number of rows. Generate series generated 10 rows. We have 10 rows. What effectively has happened, and again, it was in that description before, from each row, we have reached up and out to all of the other rows and summed it. So for each individual row, and you can't see it here, you'll see it later, for each individual row, we're reaching around to the other rows and putting a value on that row that is representative of values not only on that row, but potentially on any other row in the set. I'll say that again. That number, the number for a window function, represents not just that row, but potentially can be affected by other rows in the set. Yes? So does that add them up only once, or does it reference? Practically, I think it's doing it every time. I don't know if we optimized this case or not. I've never looked at the code. We could have in this case, but in other cases we couldn't have. So whether we do that or not, I don't remember. And in fact, I don't even think explain would tell you. You'd have to look at the C code to see whether, when we realize that the frame clause is going to affect all the rows the same, it would be pretty easy if you look at the code because you'd see a parameter that said all the same or something like that. But I've never looked at the code. Other questions? Okay. Here's our second example. Now we're doing two window functions. We're doing a count and we're doing a sum. And the count is counting all 10 rows, goes to 10 rows, we're just counting 1 to 10. To each row can see 10 rows, and each row sees a total of 55. Right? Very, very interesting. Again, both these are defaults. And I can do this. I can actually add a window clause. Here I'm adding a window clause called W, which is the default, and now I'm referencing W in both of the window clauses. This is a shorthand. If you're using the same window specification multiple times, you can give it a name and then use that name reference the name any place you want in the query. Okay? Just some syntax. I mentioned there's stuff in parentheses. Literally, this is the default meaning when you don't put anything in the parentheses. The default meaning is range between unbounded preceding and current row. Your first tar pit is the current row does not always mean the current row, literally. All right? This is probably what got me, off the wagon when I started. Okay? So, I'm going to talk about that in a minute, but just red flag that current row is not always the current row. Okay? Any questions? Okay, so let's take a look at the window syntax. So here we have the full syntax for a window function. You have an optional partition by clause. You have an optional order by clause. Then inside you have what's called a frame clause, which can say the word range or rows. And then you have a frame start or a between frame start and frame end. And the frame start and frame end can be any of these things. Again, here's the syntax if you want to look it up in Postgres. All right. This is quite convoluted. I'll be talking about all of these things in the next hour. Okay? Great. Okay, so my defaults. Range between unbounded preceding and current row. This is the default you get. Okay, so the default has no partition by, has no order by, and has the word range right here. Okay? And again, because there's, and again, this is just something I'm going to have to talk about in a minute, but range means current row defaults to representing all rows, which I'll talk about in a minute. Okay? So, current row. When you see current row, either as a default or you're literally typing current row in your query, it can mean three different things. It can mean what you and I would think it would normally mean, which is the current row. Okay? It can mean the first or last row with the same order by value, technically called peers. Okay? Or it can mean the first and last row with a partition, or the set. And depending on what other words you use in the window clause, current row can mean any of these three things. All right? I don't think this is a great design from the SQL Standard Committee, but this is the hand we've been dealt, and this is the hand that we have to play. Okay? So, literally, current row will mean literal current row only in something called rows mode. All right? If you're in rows mode, you're literally only current row. If you're in range mode with an order by, current row means the first or last row with the same order by value. I'll be showing examples of this. Dave looks like he's getting indigestion. I don't blame you. I remember going to my wife and saying, I think I finally got it. You know, like Einstein or Alexander Graham Bell. I think I finally got it. Because I just kept digging and digging and digging to find out all this behavior, which is documented in Postgres and documented in SQL Standard, but because the names don't mean what they think you mean, it's a very hard process to digest. It's like if I say that this digit means 6, right? And if I type, this and a 2, well, it's actually 62, not like the number. It's like a number that doesn't look like a number anymore. It's a different number. It's kind of the same. The current rows isn't really current row. It could mean something else, depending on what day it is, right? I mean, that's where you start to get confusing. And again, if you're in range mode and you don't have an order by, current row means the first or last row of the partition. I'll show you some examples of that. Okay. Questions? Indigestion? Okay. So let's graphically look at this. This is the literal current row right here. Okay? I'm just doing some example with some duplicates so you can kind of see what's going on. This is the literal current row. Okay? Literal current row in rows mode. This is the current row in range mode with an order by X. It's the two values that have the same order by value. Yes, ma'am. Yes. So the question is, do you have a 30-second explanation for what a partition is? I have a slide, I think back in 50-something, that actually shows you partitions. Up until we get to that slide, just assume the partition is the whole result set. Okay? So by default, if you don't use the word partition is the whole result set. So when I say here, first to last row of the partition, it's really the first last row of the result set. That's why we got 55, actually. And I'm going to show you exactly why. I'm going to walk through some examples. Okay? Great question. Other questions? Okay. This is the window frame in rows mode between unbounded proceeding and the current row. This is unbounded proceeding to the current row in range mode. Are you with me? All right. I added an extra 1 here because I went from rows mode to range mode. Right? And this is unbounded. This is the entire partition or the entire set. Exactly what you're saying here. Right? Partition. In this, there's some cases in the docs where we talk about partitions, but it's the whole set because we haven't defined one. But then there's other cases where when you define a partition, then it blocks off the set into separate partitions. And I'll show you some examples, probably in the 50, 60 slide range. Okay? Here's a better example. This is actually the SQL you would use for each case. Okay? So just written out. Rows mode, current row to current row. Bingo. Makes sense, right? Start at the current row, end at the current row. I'm in rows mode. This, order by X, range current row to current row. It's the current row from beginning to end, okay? This is rows unbounded proceeding to current row in rows mode. Order by X unbounded proceeding is this, and then this is rows between unbounded proceeding, unbounded following. Okay, graphically. Any questions? No one's ill. Good. It gets a little. We're gonna start to get through the weeds a little bit. This is not a pleasant part of the talk. It's like I don't know how to explain it. It's sort of like kind of you get in the ocean and there's all this like sand and like jellyfish are around, and eventually you get out to an area where it's nice and clear, and we're kind of getting out to that clear area, but there's a lot of jellyfish and like shells on the beach that are going to hit you in the foot and just like yucky stuff. You don't want to know what that is on the sand. Like, I don't know, like, what is that? Right? Some dead animal or whatever. That's kind of where we are, right? Okay. So, we're going to show you specific examples now, walking through what I just talked about. And I think this is going to be very clear. Again, keep your eye on the red text because that's where the differences are in the queries. So this is the query we had before. Exact same query. And remember I said that the default is range between unbounded preceding and current row. The reason this looks this way is because we're in range mode. We have no order by. So the current row is the last row in the set, or the last row in the partition. I'm going to back up again a little bit. I talked about this. Current row can mean first or last row in the partition, range mode without order by. Right? Yes, sir. Mhm. No, if you say rows between current row and current row, you get just your current row. That's right. If you say range between current row and current row, then you get all of the rows that have the same order by value. If you have an order by, and if you don't, you get the entire set. Right? I think I have an example here. You're definitely gonna be ill with that one, but I do have an example. Okay, so this is range between unbounded preceding and current row, and again, unbounded preceding, that one makes sense to us. Current row, because we have no order by, and because we're in range mode, we are getting all the way to the end. If I change range mode to rows mode, this is the first time we've actually seen specific changes on individual rows instead of the same number repeating over and over again. Yes, sir. Yes. Right. Thank you. Correct. Yes, and I challenge you to say that 3 times fast. But anyway, that is exactly it. Yes. That is it. Yeah. And yes. and, and you had to select every word as you said that to be accurate. Yes. This is why I gave up 6 years ago. Yes. And why I finally cracked it. Now this one is interesting because effectively what it's doing is it's going from the first row up until the literal current row. So 1 is 1, 3 is 2 plus 1, 6 is 3 plus 2 plus 1, 10 is 4 plus 3, right, all the way down. And the 55 is here because we know 10 to 1 is 55, right? 9 is 45. 9 to 1 is 45, right? So it's actually behaving in a predictable way here. Yeah, that would be bad, yeah. There, when I get to the section 4, there's a whole bunch of manipulation you can do where you can reach back 2 rows or forward 2 rows or really cool stuff. Yeah. I'm just starting like, let's get to the water first, right? But we're going to get to a point where you can do all sorts of cool manipulation. Right now, again, just like common table expressions, probably no one's ever going to do this actual query, right? There's no reason to. But illustrative-wise, I think it works really well. Okay. In fact, if you look at the count, it's literally telling you not the number in the first column. It's telling you how many rows it sees. Because that's what we're asking for. The second row is count. So how many rows? I see 1 row here. I see 2 rows here. We see 3 rows all the way down. It's not copying this row. It just so happens to be the same number. Yes, sir. So could in the example, could we call current row the current frame? No, because a frame a frame is effectively a beginning and end of a set. So it's really not the current frame. It's a row. The frame is literally has to have a start and an end point. So you can't say the current row is a frame because it doesn't make any sense. Yes, you can say you say current row in that case is the frame end because if you look at the syntax, that's exactly what the label says. Yeah, but I'm not sure it gets you anything. Somebody had a question here. Yes, sir. Yeah. So the question is it actually going through and actually calculating this for each one? The answer is yes. The good news is that nobody ever really complains about performance for window frames because effectively what you do is you run the query and then you run this frame macro over it, and effectively all the data's in memory. It's not that big a deal. I've never heard anyone complain about the performance of this, and it's certainly always going to be better than trying to do it in the client application. So I really would not be concerned about that. Whether we optimize certain cases, I can't remember whether we do or not. Yes, please. Yes. Yeah. 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 I understand. It's pretty minor. Yeah. Did I answer your question? I understand. Yeah, and then you're doing so. The question is if you do something iterative and it's long strings and stuff like that. Yeah, I don't know. I've never seen people do that kind of thing, but it sounds interesting. Yes, sir. Yes. Okay, so if you don't say between, then the frame end defaults to current row. Except we don't know what current row means. It defaults to the text current row, whatever that means, yes. And I'll show you some examples in future slides, which actually show me using the defaults. I haven't gotten there yet, but I have a whole bunch of slides that show you one query with the defaults and one with nothing there, and it'll default to current row always. Right? Because that, again, you can specify the beginning, and then the end is just the default. Right? Other questions? Okay. Okay. So, so here actually this is an example. Okay, here's an example right here. Default end frame. Current. Oh boy, this you must be looking at the slides, right? There we go. Right. So effectively, if you don't, I didn't even remember that was the next slide. So if you don't specify an end frame, it defaults to current row, and effectively you're getting the same result here. And I'm saying unbounded proceeding, and what is not specified but defaults is and current row, between and current row. Okay. So that's you would use the word between and then that current row over there. But that again, the same result. Okay. What if I say this? Rows, we're in rows mode because that means current row literally means current row. Okay? So rows between current row and current row, and what do you know? Every row sees one row, and the row is actually itself because it's summing itself one time. Right? Actually makes sense. And I can do this. If I say rows current row, what's the default for this end? Current row, right? So it's current row to current row. It's the same result. Current row to current row, same output, right? Yay. Wins one for the team. Here's the whole thing flipped over. Now I'm in rows mode, which means that current row literally means current row. And instead of saying unbounded proceeding to current row, I'm going to say current row to unbounded following. And I just flipped the whole thing over. I start with 55, which is 1 down to 10, and then 2 is 54 down, 3, 52 down, and then the last row is just itself. I just flipped it backward. Yes, sir. If you did rows between current row and current row, would you effectively nullify the purpose of doing a window? Well, the problem is I'm only showing you like numeric aggregates, but there's a whole bunch of custom aggregates. So I think you probably would. You probably would never want to do that because the whole value of window functions is to be able to reach around outside your current row. So if you did current row to current row and you're in rows mode, there's probably no reason to do that. I can see a reason for doing current row to current row in range mode. Or if you had a partition, yeah. Yeah, that would be another example, yeah. Yeah. Right. Actually, it wouldn't matter whether you had a partition or not. I don't think. Yeah. Well, we haven't gotten a partition, so let's just skip it. Okay. Here's our first interesting one, where we start to do something different. I'm now saying rows mode between one preceding and current row. Okay. So I'm saying I'm in rows mode, so current row literally means current row, and I'm doing one preceding. So now I find the count, and the first row has no preceding row, so it only sees one. All the other rows see two, right? If I do the count with an X instead of a star, you'll notice these are the same. The difference between count star and count X, this one will count nulls, this one will not. The point is that these missing rows are not null. They're actually just not there, and they are not counted, whether you use star or not. But what's interesting is the sum is the row plus the row before it, if there is one. So it's 3, 2 plus 1, 5, 3 plus 2, 7, 4 plus 3, 9, 5 plus 4, all the way down. 19, 10 plus 9. Okay? Kind of cool. Okay. One following, same trick, other way. All the rows see 2, except for the last one. Okay? 3 is 1 plus 2, 5, 2 plus 3, all the way down. 10 is 10 because there's no way after it. Okay? Okay. 3 preceding. Now I'm going 3 back. So you'll notice that up until row 4, you don't see 4 rows because there isn't 4 rows, 3 rows before either of these rows. So the first row only sees itself, second row sees 2 before, third row sees 3 before, fourth row finally can see 3 before and all the way down. Okay. And you'll notice the numbers, 1, 2, 3, they add up. 10 is 4, 3, 2, 1, 6, 3, 2, 1, 14, 5, 4, 3, and 2, and so forth all the way down. Okay. Any questions about that? It's pretty straightforward, I think. Okay. And again, these are, we have a whole section which actually walks through these examples and does an analysis of employees. So just hold on for that point. We have to finish this section, and then we got another section to go before we can actually get to the examples. When we get to the examples, all of this kind of comes together, and you can start to see some actual analytics on some actual data, which returns some real results. But we aren't there yet. I have to get us there, right? So let's look at order by. Remember what I said, when an order by happens, all of a sudden current row in range mode means all of the values that have the same order by value. And I'll show you some examples of that. So order by X, I've left everything as the default, and now you will see that the current range between current row, actually the current row is literally almost the current row here. Current row peers are rows that equal values to the order by columns or all partitions if the order by is not specified. Here we do have it, and we're getting a different result because we've added the order by. Yes? Yeah, what's this right here? Exactly. Exactly the same, right. So when I don't specify anything here, I'm really getting this. And when we now see the text, it makes sense. Because we're ranged between unbounded preceding and current row, I have an order by, so the current row means all of the values that have the same order by value. We have unique values here, so current row, this order by in for this data order by ends up being just the current row, but just for this data. And in a minute, I'm going to show you some duplicates, and then it's going to start to make sense. Okay, so practically for this data, it is. But I would almost tell you never to use the defaults. Just spell it out, because it feels like the defaults are so error-prone that it's really just not worth trying to use them. I realize it's a lot of text. You could use a window clause, okay, and give it a name, and then just use that name everywhere. But there's just really no value of not using these defaults, because the defaults will trip you up. And I'll show you some examples in our real-world data that will trip you up. Okay. So here's another one. Now this is order by X range, current row to current row, and because they're all unique, you basically get this output. And each row only sees itself because there are no peers. Each row has no peers. All right. In fact, as you read the Postgres docs, or really any docs on this, you're going to see terms like peers and partitions and frames and so on. And a lot of times when I hear the word partition or frame or set, I think of it the same thing. Like it's a frame, it's a partition, it's kind of the same. A set, no. In Windows, the peers, they're like completely different. They have very technical meanings. And one of the problems, I have improved the Postgres docs a little bit to Postgres 10, but even then, when you start to look at the actual text they use, you can't sort of gloss over a term and say, oh, that's the same as some other term. It sounds the same. Because they have specific meanings, and that's why I'm trying to sort of bring that out here. All right. So let's go to a better example that's going to illustrate the case for peers. And instead of going 1 to 10, I'm going to just go to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay? So I'm going to interject duplicates here. So if I now do my run just like before with the duplicate clause, the parentheses, I get each row seeing all 10 rows, and instead of totaling to 55, this set totals to 30. So 30 is our 55 now. Okay? All the numbers, 1, 1, 2, 2, 3, all the way to 5, that totals to 30. Okay. Okay. So, this is a query order by X. Now, I haven't remembered the defaults, right? So this is really order by, is really this, okay? Order by X, range between unbound C and current row. But current row, because we're in range mode and order by, means the first or last peer value. So I'm going to back up. Why did I get these numbers? Why do these jump by 2 like that? That's because each row can see all of the rows where it is peers of. So the first row can see the second row. The third row can see the fourth row. The ninth row can see the 10th row. And when you look at the totals, 1 plus 1, 2, you get 2 for both of them. 6, 6. 2 plus 2 plus 1 plus 1 for both of them. Okay? Again, 12, 20, and here's our 30 right here. But for both rows. Because unbounded proceeding to current row is the last peer value. It's not my current row. It's the last row which has the same same order by value as I do. So it goes all the way, for this row, it sees this as the end of the current row. We're good? Whoa, what happened? This was range mode. Same query. This is rows mode. What's happened? All of a sudden, I don't see the jumping by 2 anymore. I see literally 1, 2, 3, 4, 5, 6, 7, 8, 10, and my numbers are different. Because in rows mode, current row means the literal current row. Yes, sir. Yes. So question is, can you say order by X rows and not put anything for the start and end? I'm going to have to go back to the syntax. And it looks like you have to do, it looks like you cannot do that. It looks like you have to say rows unbounded preceding or rows current row or something. You can't just say rows and stop. I don't know why, but again, that looks like what the SQL standard. I grabbed this right from the Postgres doc, so I would be surprised. If this was optional, we'd have a bracket here. But because we have a brace, it's got to be one or the other. I don't know why. I don't know why it was that way. Okay. So you can kind of see in rows mode how that's working. As soon as we switch into rows mode, current row was not my peers anymore, and I start to stop my frame at the current row literally. Okay. I can do this, order by X range current row. Now this is interesting. I'm in range mode here. So what this is really is range current row to current row, between current row and current row, and effectively each row sees two rows, right? That sees 2, 1 plus 1. This sees 4, 2 plus 2, 6, 3 plus 3, 4 plus 4, 5 plus 5, boom, like that. Right? It works. It actually there's actually some logic here, right? If I switch into rows mode, here's range mode. If I switch into rows mode, again, each row just sees itself, and you're just seeing itself. There's nothing there. Okay? But when I was in range mode, I saw only my peers. But as soon as I go into rows mode, there's nothing there. Nothing interesting anyway. Okay, any questions? Okay, partitions. We talked about partitions a little bit. Again, by default, the partition is its a whole set, but you can partition your data. In this case, I'm partitioning by X, and what effectively I'm doing is I'm making each value its own partition. So this is one partition, this is two partitions, this is three partitions. And you can see each row can only see its own peers because I've created a partition. I've got 5 partitions here, okay? And it basically it's basically this same specification, okay? Now that's kind of boring, so what I'm going to do is I'm going to break it up. I'm going to say one partition is everything less than 3, and the other partition is everything greater than or equal to 3. So here's everything less than 3, here's everything greater than or equal to 3, okay? So less than 3 is red, greater than or equal to 3. Now, remember, I haven't specified anything after this, so what is my default? Range between unbounded preceding and current row. In range mode, there's no order by. In range mode, current row is the end of a partition. So now, to answer the lady's question, effectively, when I do a sum here, I am summing all of the values in marked partition. Okay, I have 4 rows. I've got 4 values here. Here I have 6 rows, and I can see all 6 of them. Okay, and effectively the total of these is 24. Right here, the total of these is 6. All right? Okay. If I add an order by, well, as soon as I added an order by, again, my default frame is range between unbounded preceding and current row. I have an order by, therefore, the current row is the last value of my peer group. So effectively, the first row can see 2 rows, the second row can see 2 rows, the third row can see 4 rows, the fourth row can see 4 rows. And the same thing down here, starts out from 0 again. Yes, sir. Yes. So the question is, in one case here, I'm passing a value. I'm just ordering by a column value, and the other case, I'm creating a Boolean. Effectively, what I'm really ordering by is 0 and 1. Again, this is Postgres. We have a Boolean type. So effectively, when I order by an expression, I'm really ordering. I'm sorry. When I'm partitioning by an expression, I'm effectively just partitioning by 0 or 1. That's correct. That's correct. That would be just 2 partitions. Now I could do modulus 10, and then I got like 10 partitions, right? Because then I would be doing a modulus, so it would be modulus 10 would be, so I could put an expression, a function call in there. I could do some kind of arithmetic. In this case, I just used a column and a boolean, but I could put anything in there. I could put a factorial. I don't know what I mean. Whatever I want to put in there. I could do alphabetics. I don't even have to use numbers. I could put like letters. I think. I'm sorry. So can you do it inside of a range clause? No. It has to be. You can do it in a partition, and you can also do it in an order by. You could order by an expression if you wanted to. So partition by X in, yes, you could use the in clause. I'm sorry, yeah, you could use anything you can use in SQL effectively. A function call, yeah, it could be anything, any expression. Well, it depends. Yes, that's right, because in would only return true and false. So in that case, you're right, you would only get two partitions. Yeah, thank you. Yes, sir. Right. So the question is, if you had a mismatched expression for the partition and the order by, how is that going to behave? I believe the order by applies within the partition itself, and it does not cross partitions. Peers have to be in the same partition. In fact, by definition, I guess I didn't make this clear, you can never cross a partition with a window function. They're like just like optimization fence for common table expressions. They are boundaries which cannot be crossed. And I'll show a bunch of examples later. So effectively, every time you cross a partition boundary, you are starting with a brand new set. Okay. And again, this expression is this, and now it makes a little more sense because it's current row, order by, it's the peers, and then you can kind of see how it looks. Now, if I go from range mode to rows mode, right? See that? Rows mode. Well, it's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Nothing exciting here at all, because the order by doesn't have an effect on current row because it's just the current row, right? So the order by is kind of immaterial here because I'm not really using any peer groups. There are some other reasons to use it. For example, for some of the window functions I'll show you later, but in this case, there's no value. This particular query is no reason. Questions? Yeah. Yeah. So the question is, if the rows weren't in order and you didn't have the order by clause, would you still get the output the same result? And the answer is no. One of the things that I'm not doing here, which I technically should be doing, is to add an order by outside of the window function. Okay? The reason I'm not doing that is for clarity. Because I'm only using one order by, the output by definition comes out in the order that I specified. It doesn't, the specification, the SQL standard doesn't really require it, but that's the way Postgres always operates. So effectively, when I only have one order by, I always get the results out. What you can do is you can have multiple window functions, all with different order bys, and you have the same query using multiple order. You don't know what result out order you're getting the result back in. And in almost all of those cases, you're always going to have an outside order by, and I would always recommend that you always have an outside order by to specify what you want it to come out as. No, because the order, I say, if you did that, okay, so the question is, if you didn't have the order by, would the sums appear the same? And you're kind of right. If the reason, you're kind of right, the reason that current row means unbounded following by default without an order by in range mode, which is the default, is because a set that doesn't have an order by effectively has no definition of where the current row is. So how would you really know where it's supposed to be? So they kind of gave you the rows mode to kind of override that and say, I don't care, I'm specifying rows mode, whatever order the rows come in, that's the way order I want to process them, right? And then current row can mean current row, but that's why I've had some discussions in different. I've delivered this 9 or 11 times since I wrote it, and one or two times people would say the reason those defaults are there is because the sets are not ordered unless you give an order by, and therefore the meaning of current row wouldn't have it make any sense of specifying the frame, and that's why you have to say rows mode when you really want to override this non-ordered value of the set, or add an order by in there, and then the rows mode, then there is an meaning for current row because you have ordered it. So I'm kind of backing into the answer, but effectively that's the reason the defaults are the way they are. Even though they're practically inconvenient, that's the reason that almost every case you're going to want to specify an order by, even if you're using rows mode, because you want to make sure you're getting the the data in the order you need to process it. And when you start to mix different, you can have multiple window frames in the same query, and then everything else, everything goes out the window because you don't even know what order you're getting your results back anymore. Yeah. So that's a lot more detail than I can normally give, but you're absolutely correct. There's a reason that default is there. It's because the ordering is indeterminate without an order by. Yeah. So, other questions? Okay. Window-specific functions. So up until this point, I've shown you only things like count and sum and average, things you've seen already. But there are a bunch of window functions that are designed just to be used with windows, a bunch of aggregates that are designed just to be used with window functions. Very, very powerful. So first one, row number. All it does is to number the results. So here's my table, and here's the row number for each one. Okay. Now, one aspect you should notice here, row number takes no arguments and operates on partitions, not window frames. I have a slide later that summarizes this, but every time you look up a window function in the manual, it will say operates on partitions or operates on window frames. There's a whole bunch of functions that don't care what window frame you define. They operate on partitions. So you can go range mode, rows mode, unbounded proceeding until the cows come home, and you're going to get the same result from that function. And that's what I was saying. When you're reading the manual, be very clear what you're, what you're looking at, okay, and how that particular thing operates, because they're going to be different. All right. Okay. Another one, lag. Lag is a row before my current row. Okay? So in this case, 1, there is no row before it, so it returns null. All the other rows just shifts them down by 1. Okay? So this is, again, a window-specific aggregate. It can only be used with an over function, with a window clause, window function. Okay? And it's always the row before. All right? And you can do lag 2. Give me 2 rows before. And again, returns null for the rows that don't exist. I can do lag and lead. So here's the rows 2 rows before. Here's the ones 2 rows after. Okay? And the same qualification I gave you earlier, these operate on partitions, not window frames. Doesn't care about rows mode. Cares about order by, okay? But doesn't care about between or unbounded or any of that stuff. Just doesn't care. Okay? And you can define defaults for non-sister rows. First value, last value. Give me the first value within the, help me here. What? The frame, right here. This is our first window-specific function that deals with frames, not with partitions. Right. All these other ones operate on partitions. This one operates in frames. I have a slide at the end. Don't have to remember it. It's like a big slide. I have all this stuff in one slide. I know people they pull up my presentation just to see that one slide, right? Because you forget. But this one operates on window frames. So in fact, the order by the frame I specify actually makes a difference. Okay. Now, why is that important? Because look, first value, they seem to work just fine. Like first value, it knows the first value is 1. Last value, not so much. Why is it doing this? Somebody want to explain this? Current row is the default end frame, and that's why, exactly. Unbounded proceeding is the beginning default, but the last row is the end of the frame default is current row, and current row in range mode with an order by are my peers. So literally, this number is really that number, with this number, right? Because it's seeing the end of and that's why it's kind of hopping along as the window frame gets bigger. As current row moves down, my last row, I can see more. My window frame is getting bigger. Yes, sir. If there's no order by, the whole thing, yeah. If there's no order by, then this is all going to be 5s. So, or if I go into rows mode, right, and I do unbounded proceeding and unbounded following, I get the 5s. Okay? So again, if you're using last value, keep in mind it's using frames. You may want to specify this kind of thing. Because you probably don't want this for last value. You might. But just be aware of what you're asking for. This is why I'm saying don't use the defaults and write what you want, because the defaults can trip you up so much. Okay? Here's another window function, nth value. It gives you the nth value in the set. So these operate on frames, right? So the first 2 rows don't see a third row in their frame. Only at the third row does it see a third row in the frame. Same thing over here. It doesn't see a 7th row until row 7. Because I'm using the defaults. If I do that, range between unbounded proceeding and current row, I get this. This is my default. I get the same thing, right? But now if I go rows between unbounded proceeding and unbounded following, bam! I see the 3rd row right away. I see the 7th row right away. Right? Be aware of what you're asking for. Every time you use a function, is it a window function? Is it using frames? Is it not using frames? If it's using frames, what's my window frame definition? Rank and dense rank. These are cool. Not so much in this slide. What it's trying to do is rank my values. But you know, without an order by, there is no rank. Even though it's operating on a partition, it kind of doesn't know what the order is, so it's kind of useless. And even if I specify the frame, it's operating on partition, so it doesn't matter. It doesn't make any difference. If I go to rows mode, it still doesn't make any difference. Okay? But when I add an order by, now this starts to make sense. What it's trying to do is to take my values and rank them. Now, there's 2 types of rank. If 2 people cross the finish line first at the same time, they're both first. What's the next person's rank who goes across the finish line? Or 2, right. Both answers are right. There are 3 if you consider that the 2 people who went first really take the first and second spot, and the guy's third. He literally is third, right? Because I had 2 before him, her. Or I might want to not have a gap, and I want to have that person second. So rank will basically leave a gap. These 2 people finish first because they got the first thing, then third, then fifth, and sixth. This one, I got 2 first place people. I have 2 second place people. I have 2 third place people. That's dense rank. It's rank and dense rank. Okay. percentile, percent rank, and cumulative distribution. These are trying to give me a sense of what percentage of people are less than me, or what percentage of people are equal or less than me. The gory details are down here. Effectively, one of the odd things is that with percent rank, it excludes yourself. And there's some reasons for that, particularly because if you have one person who's highest, there's really no one less than him, so he's really greater than 100% of everybody, but if you count him or her, then you're like, that's not really 100%. So there's all the goofy things going on. Cumulative distribution is a little easier because you include yourself, so therefore 100% of the people are equal or less than me. 80% of the people are equal or less than me, all the way down. Okay? I put a blog entry about this. In fact, I don't really like either of these. I'd love to have a function that considered everyone less than me and half of the people equal to me. I think, because if I get an SAT score, I want to know how many are less than me, and then let's assume half of them are less than me. Right? That would be a better number, but there's no name for that, and we don't support it. I guess somebody could write a version of that, but that's just, again, I have a blog entry about it. Finally, for n-tile, I'm trying to break everything up into 3 parts. So here's my first part, here's my second part, and here's my third part, in terms of chunking my groups together. Okay, again, based on the order by. If I add a partition, again, same partition we used before, what I get is here, these people are first, these people are third within that partition, then the rank starts over again. This is a great illustration of the way partitions work. In the new partition, these people are first, these people are third or second. Okay? Partitions, you never cross partitions with these window functions. Here's another example with percentile rank, cumulative distribution, and n-tile, again, using partitions. Again, starts off at 0 for the second partition. All right? Okay. Any questions? All right, so now we're getting to the meat. We've gone through all that sand and jellyfish and everything, and now we're going to actually look at an actual example, and we're going to apply window functions to this example. Okay, and I'm going to show you analytics, and I'll show you why you do it this way. And again, the idea is you're not going to be copying a window function from someone else. You actually, by the end of this, are going to be able to use and write your own window functions, knowing what all these things mean, knowing what all the defaults mean, knowing whether your functions operate on frames and partitions and what order by does and all that other stuff, so you're not going to get surprised. Okay? Okay, so we have an employee table, and we have 1, 2, 3, 4, 7 employees. Okay? Again, they have a department, and they have a salary. Okay, so very traditional example here for employees. And we do a select on the employee table, and we effectively have 7 employees in different departments. Yay, 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 yay. Okay? Okay. Now we do an aggregate. Now this is not a window function. We're just going to do a traditional aggregate. So count how many employees do we have? 7. Total salary, this. Average salary, that. No window functions here. There's just straight aggregates. I can do a group by. I can get the number of people in each department, and I can get the sum and average for each department. Wonderful. But again, not a window function. I've lost the distinctiveness of my employees. They're now grouped together into a slush of one line per department. And we talked about the idea of window functions giving us the ability to maintain distinctness of these rows. That's what we're going to show you today. Here's another one, roll up. This is still not a window function, but it does give me the option of getting totals by department, and then a final line which has the roll up of all of the rows together. Still not a window function. Okay. So here's our employees again, ordered by salary. And here's our first window function. We have the names, we have the salaries, and then we have the sum. The sum with the notorious open-close default number there with the sum. And remember, we used to have 55 all the way over here. Now we got 40,200 all over there. Right? Doesn't look very useful, does it? Right? We maintained the 7 distinct employees, and now we got the same salary on all of them. What good is that? Well, we can actually make some use of that. Here's an example. We can take that window function and we can divide the person's salary by the window function and we can multiply by 100 and round it to 2 decimal points, and now I can see the percentage of all salary for each employee. Isn't that cool, right? Instead of showing 55, yeah. Sorry? Right. Instead of showing 55, now we can actually use that number and get a percentage. It's kind of nice. Okay? And here's an example where we actually do cumulative totals. Now, this is not very useful in this case, but what we're doing is we're using order by unbounded proceeding to current row, and because we're in rows mode, we're effectively moving down, and it's getting higher each time. Now, this is probably useless, but if you did have like cumulative totals for a time series data, like how much rain this month, and each day you want the total for the month, that would be a good example. Okay. Keep in mind, I am using rows mode here. When I originally wrote this query for this talk, I used the defaults. Why is that wrong? Bingo. Andy and Sandy have the same salary. Therefore, they would have the same sum. That is probably not what I wanted. Somebody pointed that out during a talk. Yes. Yes, I had to apologize, and I fixed it, and I said it was up in the next hour, and I got bitten because I was so focused on showing you examples that I didn't do what I told you about showing the defaults. Very interesting. Learn something. Here's another one. This is a window function showing the average of each employee. Sounds useful, but again, it's the average on the same thing. What good is that? Well, as you might imagine, I can actually subtract the person's salary from the average, and everyone in red is above average in salary, and everyone in blue, unfortunately, is below average in salary. Kind of nice, right? Much easier to do this than try and do it in my application. What about this? Instead of comparing the salary to the average, I want to compare it to the next salary. The next salary forward, okay? Because I'm ordering by salary descending. So how much more is Mike making than James? How much more is James than Betty? How much more Betty than Sandy? How much more Sandy than Andy? Okay? How much more Andy than Tracy? How much more Tracy than Carol? You get the idea. Okay, so instead of comparing to the average, I'm comparing to the next person who has the next highest salary. Yes? So shouldn't Sandy and Andy show the same thing? You don't get it. You're not getting it. These operate on partitions. So they have no peers. It doesn't matter. No, not with lag. No, they would always have different, because you're with lag and lead. You're literally always accessing the next value. So, yeah, it wouldn't. No, not the next peer group. No, that's a good point. Yeah. Yeah, and you could do that maybe with partition by or something. I'm not sure. That maybe that would be a way of going at it. Yeah. Yeah, I don't know what these numbers are. They're like just like I don't know if they're monthly or yearly. I don't know. I just picked something that rounded well because they come to nice numbers. So now this is interesting. This is kind of going a little meta analysis. We're comparing the person's salary, how much more that person is making than the least salaried employee. Okay. And then we're making it what percentage they are more than the least salaried employee. You sometimes see this type of analysis for corporate environments. So here, this person is making 25 more than the last person and 54% more than whatever. You get the idea. And I have used a window clause because I needed last value, which is a frame clause, to see this bottom value. Okay? Okay. I can do rank and dense rank. So here's the rank of the employees. You'll notice that Andy and Sandy make the same amount of money, so Tracy is either 6th or 5th within that set, whether you do rank or dense rank, right? Makes sense. I can do departmental average. I can compute the person, their salary, the average of the department, and how much more or less that person is making than the departmental average. All right? And I'm doing that by creating a partition by department here, and then I'm computing the average within that department, but I'm computing their salary minus the average. All right? Kind of interesting. Yeah. I don't know what that question is. I'm sorry. I can't understand what you're asking. Like, let's say you wanted to omit James from the list, but you wanted Andy and Tracy to go to the line 800. You could do it. You could do it in the where clause here, I think, because these over clauses aren't really affected by the where clause. Yeah. Yeah. Yeah, because they're sort of independent inside of there. Yeah. Mm-hmm. So the question is, could you exclude somebody and still have them in these calculations? Absolutely, you could. So here, instead of saying partition by department to partition by department, I can create a window called D and then specify D in these cases, right? Kind of pull it together a little bit. I know I was going to need those extra 5 minutes, so just hold on here. We are very close to being done. So instead of comparing the person to their to the department average, we can compare the person to the next salary within that department. Not compared to the average of the department, but the next salary of that department. So Mike is 800 more than Betty, Sandy 800 more than Carol, but again, James 1,200 more than Andy, Andy 800 more than Tracy. So you get an idea of how they're breaking up within their departments. Okay, again, comparing to the average department, comparing to the next highest salary department, different numbers. This one is really interesting. I can find the person's rank within their department using S, and also their rank within the company. So here is the rank within their departments. Here is the rank within the company. And a good example of using different window clauses in the same query. All right. Interesting. Okay, any questions? So I just want to end with sort of an overview of things you need to remember, to gel it in your head, and we can all head out. First, when you're setting up a window function, do you want to split the data? You're going to need a partition. Do you want an order to the partitions, to the value in the partitions? Okay. Use order by, right? How do you want to handle rows with the same order by value? Range mode or rows mode? Rank or dense rank, right? A lot of times people writing window functions get caught up and don't test for duplicate values. When duplicate values show up, they get the wrong results. And you don't want somebody waving a sheet of paper in front of you saying, this number is wrong, and then you have to figure out why, and you've forgotten something. And it has happened to me. Okay? Do you need to define a window frame? Maybe you're going to use it multiple places. Window functions can define their own partitions and ordering in window frames. So you can have multiple different window frame and ordering partitions in the same query. They're independent. Okay? Multiple window names can be defined in the window clause. You can define multiple times, and then pay attention to whether a window function operates on a frame or a partition. The documentation is going to tell you that. So this is the slide I promised. It basically shows you that some functions operate on frames, some operate on partitions. For the frame example, some of them are generic arrays like sum and average. Some of them frame operate on row access, first value, last value, and nth value. Again, operate on frames. These functions all operate on partitions. Again, some of them are related to row access, some of them are related to ranking. Okay? And again, feel free to get this slide when next time you have to roll up your sleeves, because this is a nice handy thing to have. Okay? In terms of what we have implemented in Postgres 10 and Postgres 11, we are adding some things to Postgres 11. Effectively, we are allowing a range to specify peer groups whose values are plus or minus the specified preceding or following offset. What that effectively means is you can go backward or forward based on how many peer groups are before you. If you looked at my example, every time we did following and preceding, we were in rows mode. If you do following or preceding in range mode, that's what the behavior you get. And you'll get an error in Postgres 10. Postgres 11, that'll work. Also, we now have a groups clause, which didn't exist before, in addition to range and rows, and that allows me to specify the number of peer groups plus or minus the current peer group. This one is plus or minus the specified offset in terms of a literal value, like a numeric value, plus or minus 10. This one, how many peer groups are before my current row, okay? And finally, we have a frame exclusion clause, which you can now use after your partition frame, which allows you to exclude things like the current row, exclude your current peer group, or exclude other peer groups to sort of filter out different results, okay? So that is it. Again, I apologize for going a little over, but I wanted to give you a good 20-minute break. I also didn't want to cut off any of your questions. So I think we've had a good discussion. It really has worked well in terms of allowing you to understand it, and hopefully you're going to go home and make better use of your SQL engine to do analytics, to do imperative kind of operations with common table expressions with a lot more confidence. So again, these slides are on my website. Feel free to download them at any time or take a look at what else you have. And I hope you enjoy the rest of the conference. So thanks. anything with the Postgres key.